Hello and good afternoon. Welcome to, excuse me, Wednesday chemistry lecture. Um, Today we're going to be wrapping up Lewis structures, and then moving on to VSEPR geometries. I had a few people ask me questions about what was it? Lab exercise 5, and lab exercise 5 covers three things. Just to give you the heads up, it's you'll need to be able to draw Lewis structures, assign VSEPR geometries, which is what we're headed to next, and then assign hybridization, which comes after VSEPR. So there's no due date right now for that assignment because it's a little bit. I'm not exactly sure how long it'll take for us to cover that material, but just so you know, I would start working on it once we've covered VSEPR. We should be starting that today, probably wrapping it up. On Monday. But anyways, without further ado, let's go ahead and dive in to today's lecture. So we've been talking about Lewis structures, and as of right now, we have covered everything that you're going to see with respect to Lewis structures. We know how to draw them. We know how to minimize formal charge, and how to determine the best resonance structure for a given molecule that we're drawing a Lewis structure for. So let's go ahead and dive in with a few more examples. Then we'll transition to VSEPR. Whoops. All right. Whoa. That pen's a lot finer than I like it. Okay, there we go. All right, so let's do a few more Lewis structures, starting with, let's draw the Lewis structure for sulfate. SO4 with a charge of -2. Actually, I need to open up one more layer. There we go. All right, so let's draw the Lewis structure for sulfate. We have to start by totaling our electrons. Sulfur has 6 valence electrons. Oxygen also has 6, but we have 4 of them. So that'll be a total of 24. And then our charge of -2 means that we have 2 more electrons than we should, than is normal for this collection of atoms. So we have to add 2 electrons to the count. So that brings us to, 32. We've got 32 electrons in our budget that we have to spend to construct this Lewis structure. Now, when it comes to picking a central atom, we're going to roll with sulfur, and we're rolling with sulfur because it's a third period element, and we know that third period elements can break the octet rule if need be, so it can make the most bonds. Definitely can make more than oxygen. All right, next, we need to attach all our other atoms to our central atom. We've got 4 oxygens to attach, and we know that each bond we make costs 2 electrons, so this is going to spend 8 electrons from our budget, leaving us with 24. All right, 24 electrons. Now, each oxygen here has access to 2 electrons. Now we need to complete our octets, right? And each oxygen has access to 2 electrons. It needs a total of 8, right? So each oxygen needs 6 electrons, and you'll notice we have 4 oxygens. 6 times 4 is 24. So we actually have enough electrons in our budget to complete the octet for each oxygen present. So 1, 2, 3, 4, 5, 6. I don't need to count these, but I do need to draw them all 24 dots. All right, now at this moment in time, we have completed all our octets. Each oxygen has access to 2 electrons in a bond, plus the 6 lone pairs. Sulfur has 4 bonds, so everybody has a full octet. What remains to be done is we need to assign our formal charges and then minimize our formal charges, right? Find the best resonance structure. Now, if we calculate the formal charge of any one of these oxygens, I'm just going to calculate this one. Oxygen, when it's neutral, has 6 valence electrons. When you're calculating formal charges, you count 1 electron per bond and then all of the lone pairs. In this molecule, so we subtract, oxygen has 1 electron, right, for its 1 bond, plus another 6 in lone pairs. So the formal charge here for oxygen is 6 minus 7, or -1. You can repeat this calculation for each oxygen in this molecule, and because each oxygen has 1 bond and 6 lone pair electrons, they'll all come out to have a charge of -1. Now let's calculate our formal charge for sulfur. All right, now with sulfur also has 6 electrons when it's neutral. In the structure as drawn, sulfur has no lone pair electrons and 4 bonds. So 6 minus 4 is +2. So sulfur has a formal charge of +2. All right. So this is the resonance structure this is a resonance structure for sulfate. Now we need to analyze it to see if it is the best resonance structure. I'm going to redraw it here on this new slide. So just redrawing what we had previously. So each oxygen with 6 lone pair electrons. All right, and each oxygen has a formal charge of -1. Sulfur has a formal charge of +2, as drawn. Now, the way you minimize formal charge, we said that if you have a positive charge on a third period element, and we do, coupled with a negative charge, that formal charge can be lowered if you take one of those lone pairs and use it to make a multiple bond between the negative element and that third period element bearing a positive charge. And you'll notice I'm using the resonance arrows because I'm drawing a resonance structure. Now, that's a good reminder for me to not lose my phone, mute my phone. Now, 3 of these oxygens in this new resonance structure have not changed. So I'm just going to redraw them as they existed. And because they haven't changed, they all have the same formal charge. However, this oxygen, the one on the very right, has changed. It is now double bonded to sulfur, so we need to calculate our formal charges again for this structure and see if there's more work we can do. All right, now looking at sulfur has 6 lone pairs when it's neutral. In this structure, it has 5 bonds and no lone pairs, so there's 1 electron per bond, leaving us with a formal charge of +1 for sulfur. When you look at oxygen has 6 electrons when it's neutral, minus oxygen gets 1 electron per bond and it has 2 bonds, so there's 2 electrons from bonds, plus it has 4 electrons in lone pairs. 6 minus 6 is 0, so this oxygen has a formal charge of 0. All right, now, sorry, I need to clear some space to make room. Now you'll notice that we still have a situation where we have a positive charge on a third period element adjacent to a negative charge. All right, that is the condition, that is the situation where formal charges can be minimized. So we're going to take one of those lone pairs, turn it into a double bond between this oxygen and sulfur, and see where that gets us. So again, 3 of these oxygens have not changed from the previous resonance structure to this new one. So I know that the oxygen on the very right will have no formal charge, and these two, the vertical oxygens, will have charges of -1. We now have a double bond between sulfur and the oxygen on the very left. The oxygen on the very left has 2 lone pairs. Now if we calculate this oxygen's formal charge, has 6 electrons when it's neutral, minus the 2 electrons for its bond, plus the 4 it has in lone pairs, means we have a formal charge of 0 on this oxygen. Now when we calculate sulfur, sulfur has 6 electrons when it's neutral. In this structure, it has 6 bonds and no lone pairs, so 6 minus 6 is 0. So now sulfur is neutral, and this is our best resonance structure. I know that the resonance structure cannot get a lower charge because when I look at the total charge, formal charges in this structure, I've got 2 negatives, and my molecule has a charge of -2. So you'll never have a lower charge than -2. And I know between oxygen and sulfur, sulfur is less electronegative, oxygen's more electronegative. The best resonance structure will put negative formal charges on the more electronegative elements. So I'm good to go. This is the answer to this problem. Now, I want to stress something, all right? So I wrote this and boxed it as my answer. But what if, instead of this, you had done, wait, let's throw my formal negatives on there. What if you came up with this as your answer? Kate, I'm actually getting to that question right now, actually. You might have come up with this as your answer, or possibly you could have come up with this as your answer. Takes a while drawing all these dots, but it's the only way to get the correct answer, so we have to. Right? And there's more. They could be both be, or actually there's one more. I'm just going to go ahead and draw it for completeness sake. All right. Turns out all of these structures are resonance structures of each other, and they are all equally correct. All right. All of these structures are equally correct because, remember, a Lewis structure only tells you which atoms are attached and how. Which atoms have double bonds, single bonds. Which atoms have the number of lone pairs, etc. But they do not convey anything about the shape of the molecule. Lewis structures tell you how atoms are bonded to each other in a molecule, but they do not tell you the shape of the molecule. And so you could draw any one of these 4 and they would all be equally correct. These are what we call equivalent resonance structures because they all have formal charges minimized. They all have the negative formal charges on the most electronegative elements, and they all meet the octet rule. So if you drew any one of these, it'd be perfectly correct. Even if you didn't do the exact one where I drew the two pi bonds horizontal, they could be both vertical, they could form an L, or, whatever. But they would all be equally correct because they all exhibit the same features of the best resonance structure. And it turns out there's 4 equivalent resonance structures for sulfate. So, yeah, that is it. All right. Let's see. Okay. I want to give a warning. One last parting heads up. And to do that, I'm going to actually do a structure that we've done previously. I want to revisit the Lewis structure for nitrate. All right, there's a trick in this one that a lot of students make. A lot of students make this mistake in exam contexts. So let's go ahead and draw the Lewis structure for nitrate. First, nitrogen has 5 valence electrons. Oxygen has 6, and we've got 3, so 3 times 6 is 18. And then we have our negative charge, which brings 1 extra electron to the party, giving us a total electron budget of 24. 24 electrons. All right, now, nitrogen's our central atom. It likes to make more bonds than oxygen. To attach our 3 oxygens will cost us 2, 4, 6 electrons. All right, so this leaves us with 18 electrons left to spend. You'll notice that each oxygen needs 6 more electrons. We've got 3 of them, so 3 times 6 is 18. So by completing all of our oxygen's octets, we'll spend the remaining number of electrons left in the budget. As we saw before, we have a problem. Nitrogen does not have a full octet, so we're going to remove 2 electrons from one of our oxygen in order to turn that into a double bond. And now we can assign our formal charges. If we look at this oxygen, when it's neutral, oxygen has 6. There are 2 bonds here, so you get 1 electron per bond, plus the number of lone pairs. So this oxygen has a formal charge of 0. If we look at this oxygen, again, 6 when it's neutral. This oxygen has 1 bond, so that's 1 electron. It has 6 electrons worth of lone pairs, so this oxygen will have a formal charge of -1, same as this one. And then nitrogen, when it's neutral, has 5 electrons here. It has no lone pairs and 4 bonds. 5 minus 4 is +1, so nitrogen will have a formal charge of +1. Now, here's where often students make mistakes. I'm just going to draw in my charges. Given what we've talked about with minimizing formal charge, students will be like, wait a minute, there is a positive charge. Well, okay, first off, I just want to make this explicitly clear that what I'm about to do is wrong. All right, do not do the thing I'm about to do, and we'll talk about why it's wrong. The mistake is, oh, negative charge, positive charge, I know how to minimize that. I'll take a lone pair and make it a double bond. That would give me a Lewis structure that looks like this. there. And if you calculate formal charges for this structure, you'll only have one, so you think, oh, I've minimized formal charges. This is better. But this is wrong. This nitrogen is wrong. Because nitrogen is on the second period, which means it can never break the octet rule. And in this structure, this nitrogen has 10 electrons. Whoa, not 18. And nitrogen never, actually, let me drop this down here. Nitrogen never breaks. Never breaks the octet rule. All right, so this is dead wrong. Minimizing formal charges is great, but you have to remember that you can only do that if you have an element that is on the third period or lower that's allowed to break the octet rule. Never do it for a second period element. All right? Okay. With that, that brings our discussion of Lewis structures to a close. You can now tackle any Lewis structure I can throw at you. You definitely want to practice it, get your reps in, but you can handle it now. So hit up those homework problems, and we're going to transition to VSEPR. All right, VSEPR theory. Now, let's talk. Okay, so Lewis theory was great. Lewis theory gave us really our first introduction to molecular structure, to start thinking about, okay, how do these atoms attached? Which ones are attached? How are they attached? Are they double bonded, single bonded, triple bonded, etc.? And really moved us beyond looking at atomic electronic structure to molecules. But the one downside to Lewis structures, and we've talked about this, is Lewis structures do not Lewis structures do not give let's see. No, I should say Lewis structures do not communicate. Nope, communicate's the wrong word too. I should say do not reflect. There we go. Do not reflect molecular shape. All right, they don't reflect molecular shape. Take, for example, the molecule of methane. If you draw the Lewis structure for CH4, it comes out like this. All right? And the fundamental problem with a Lewis structure is it's drawn. We're drawing a depiction of a three-dimensional molecule in a two-dimensional plane, right? We're drawing it on a piece of paper, which only has two dimensions, but a molecule lives and breathes, if you will, in a three-dimensional space, just like we do. If you look at the angle formed by the bonds here, all right? If you measure this angle, kind of using carbon as the central point, and then the two bonds here between this hydrogen, this angle comes out to be 90 degrees, right? That is a right angle, and that is the farthest that if you have four things attached to your central carbon, that's the farthest that those four atoms can get away from each other in two-dimensional space. Now, why am I talking about these bonds wanting to get away from each other? Remember what a bond is, all right? A bond is two electrons. There's two electrons in every bond. Electrons are negatively charged, and as we know, like charges repel each other. They push each other away. So every single bond that you draw is this pocket of negative energy that pushes away from every other bond, every other pocket of negative charge. I said negative energy. I meant to say negative charge. They want to get as far away from each other as possible, and in two-dimensional space, 90 degrees is as far as that can get. But it can get farther if it's allowed to exist in a three-dimensional space. All right. The true structure for methane looks like this. In three-dimensional space, the bond angle is 109 degrees. It can actually get 109 degrees apart. And the reason why is you may be going, well, if you widen that angle, won't it just smush the other two hydrogens? The answer is no. Because one of those hydrogens comes out of the board towards you, and the other goes back behind away from you. All right? This is how these three-dimensional molecular depictions are drawn. When you have a wedge, like we do in salmon, that wedge means it is coming out of the page towards you, or out of the screen, as it were. And when you have that dashed bond, as depicted in blue, that means that that bond is going away from you. And if you take any two H's and use carbon to measure the angle that they form, it'll be 109 degrees between all of them. They all have the same bond angle. All right. Even though this one looks shorter, it's just a matter of the perspective, because you're looking dead on. One's coming at your face and one's going away from your face, kind of like that. I don't know. It's hard to depict with the webcam. So this is what I have drawn here is a three-dimensional representation of the molecular structure of methane, of CH4. And this is where we're going to take the information given to us by our Lewis structures, which is which atoms are connected to which and how they're connected, and use it to develop an idea of the three-dimensional shape of each molecule. And this is called VSEPR theory. All right. So what does VSEPR stand for? It's valence shell electron pair repulsion theory. All right, that is what the VSEPR is. It's the valence shell electron pair repulsion theory. All right, and it has one very basic premise, and that is this: because bonds are all negatively charged. All right, because bonds are all negatively charged, they repel each other. And will stay as far away as physically possible in three-dimensional space. All right, because bonds are all negatively charged, they repel each other and will stay as far away as physically possible in three-dimensional space. That is the kind of the crux of VSEPR theory. That's what it's all about. All right, now we're going to take that information and use it to determine, kind of develop molecular geometry, so we can start understanding the shapes these molecules have. And we're going to be doing this based on the Lewis structure. So as we do, this kind of VSEPR analysis, there's a few things that we're going to use to analyze. So first we're going to have the Lewis structure. Next we're going to have something called electron groups. Depending upon the book that you're reading, these are sometimes called electron domains, sometimes they're called charge clouds, etc. We're going to have lone pairs. Those are self-explanatory. Then we're going to have what's known as the molecular geometry. Oh, sorry. Well, yeah. Actually, before we get to molecular geometry, we're going to have something called the electronic geometry. Followed by the molecular geometry. All right, and then finally, we're going to have the three-dimensional representation plus the bond angle. All right, so just so we can get on the same page here. Whoa. All right, let's do a little breakdown of what each of these things mean. First, the electron groups right here. This is the number of atoms plus, or the number of atoms attached to the central atom plus the number of lone pairs on the central atom. All right, and just to be clear, just so everybody knows, LP, when I write LP, that means lone pair. Lone pair of electrons. All right, so that is what the number of electron groups are. It's the number of atoms attached to the central atom plus the number of lone pairs on the central atom. Here for LP, we're talking about the lone pairs on the central atom all right. Next, for the electronic geometry, we're talking about the shape made by all electron groups around the central atom. All right. When we talk about molecular geometry, oops. The molecular geometry is the shape made by all atoms around the central atom. All right, so the electronic geometry, the shape that all electron groups make. Molecular geometry, just the shape of the atoms. All right, and then the three-dimensional representation and bond angle, we'll talk about those when we get to them. All right, the color coding here is purposeful because the electron groups around your central atom, will determine your electronic geometry, and then the number of lone pairs around your central atom determine your molecular geometry. All right, so with that in mind, let's begin to look at the different VSEPR geometries that you will run into this semester. It's a hard word. Okay, so let's go ahead and start with carbon dioxide. All right, let's look at carbon dioxide. All right, so I'm a little cramped here, so I'm just going to go like this. Here's a Lewis structure for CO2. All right, and carbon dioxide has, so to determine I will commonly I'll ask you to, what's the bond angle, or what is the molecular geometry around the central atom in a given molecule. To answer that question, you first need to determine the number of electron groups, which is the number of atoms attached to the central atom plus the number of lone pairs on the central atom. Now for CO2, there are 2 atoms on our central. And here's the thing, I'm not asking about total lone pairs, I'm asking about lone pairs on carbon for this molecule. And there are no lone pairs on carbon. So we have 2 electron groups and 0 lone pairs. All right, now when you know the number of electron groups, you can determine your electronic geometry immediately. If you have 2 electron groups around your central atom, your electronic geometry is linear. All right, always. Now, when you have 0 lone pairs means that your electronic geometry will equal your molecular geometry. Every time you have 0 lone pairs, they're the same. So for this molecule, our molecular geometry is linear. All right? That means that the 2 groups we have around our central atom will form a straight line. They get as far away from each other as possible. And our bond angle here is 180 degrees. All right? So this is the 3-dimensional representation of CO2. It's just a straight line. The 3-dimensional representation is actually 2-dimensional in nature. And it has bond angles of 180 degrees. All right? Let's look at formaldehyde. So here's a Lewis structure of formaldehyde. All right, let's count our number of electron groups. Well, we have 3 atoms attached and no lone pairs on carbon. So we have 3 electron groups, 0 lone pairs on our central atom. You'll notice that the electron groups are atoms attached. It doesn't matter if they're double or single bonded. We just want to know just the number of atoms, right? 3 atoms attached, no lone pairs. Whenever you have 3 electron groups around your central atom, your electronic geometry is trigonal, planar. All right? It's trigonal planar, and it's called this because I actually want to bump this bond angle up here. So I have a little more room to work. It's called trigonal planar because the 3 groups around your central atom, well, it's trigonal because there's 3 groups. The farthest that 3 groups can get from each other is 120 degrees. So trigonal planar geometries kind of make this peace sign, all right? And if you know your electronic geometry, you can draw where those bonds, where those groups will fall around the central atom like I just did. All right? Now, we learned that when you have 0 lone pairs, your molecular geometry and electronic geometry are the same. So our molecular geometry is trigonal planar. And now you'll notice that I've drawn the trigonal planar shape, right? Those 3 groups as far away from each other as possible. Now I just have to draw in the H's and the O. So this is the 3-dimensional representation of formaldehyde, and the bond angle here is 120 degrees, because when you chop up 360, a full circle, into 3 separate groups, it comes out to 120. All right? Now, let's do another example. Let's look at nitrite. And this is the Lewis structure for nitrite. Now let's look at our number of electron groups. Now, nitrogen, our central atom, has 2 atoms attached and 1 lone pair. So we have 3 electron groups around it, one of which is a lone pair. Now, every time you have 3 electron groups, your electronic geometry is going to be trigonal planar automatically. All right? And because we're trigonal planar, we know that the 3 electron groups are going to try to get as far from each other as possible. They're going to make that peace sign. All right? This is the first example where we have a lone pair. That means our molecular geometry and our electronic geometry are different. All right? Let's look at how it affects the molecular geometry. Now, remember we said the electronic geometry was the shape that all groups around our central atom make, whereas the molecular geometry is just the shape of the atoms. All right. So to find the molecular geometry, I often find it easiest to draw in the groups around our central atom and then figure it out. So nitrite has 2 oxygens and 1 lone pair. Those are the 3 groups around our central atom. One of those oxygens is double bonded. The other one has a single bond, 3 electrons, and a negative charge. All right. Now, so we've put all our groups on. We know our electronic geometry. Now we have to figure out our molecular geometry. And remember, molecular geometry is the shape that only the atoms make. So what I'm going to do to my central atom is take my lone pair electron group and just turn that into a pair of dots around my central. Because I'm just looking at the shape that these 3 atoms make. And when you look at it, it kind of looks like a bent line, right? Like you're going like this, and then it kinks that way. And because of that, the molecular geometry for this molecule is called a bent geometry. All right? It has a bent geometry, and this will happen every time. You will get a bent geometry every time you have 3 electron groups and 1 lone pair. Every single time. 3 electron groups, but one of them is a lone pair. You will have a bent molecular geometry. Now, let's talk about our bond angle here. The bond angle of a trigonal planar bent geometry. Now, the thing is, when you have a lone pair on your central atom, it affects the bond angle. If you have a pure trigonal planar molecular geometry, the 3 groups are all repelling evenly. They're all 120 degrees from each other. All right. When one of them is a lone pair, that lone pair, those are 2 electrons that are just centered on that nucleus, right? In a bond, the electrons are bouncing back and forth between 2 nuclei, right? The electrons are going bump, 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 bump. But when you take that second nucleus away, the electrons are spending all their time around the one nucleus, and they push harder, they pinch down on the bond by 2 degrees. So instead of a pure 120 degree bond angle, the bond angle here is 118, all right? It's pinched down 2 degrees. It's slightly smaller than a pure trigonal planar geometry. All right, so when you're trigonal planar and bent, your bond angle is 118 degrees. All right? Okay. Let's take a look at what happens when we start getting 4 electron groups in play. And we're going to do that by taking a look at methane. CH4. All right, now, we have the number of electron groups around our central atom. We have 4 electron groups. There are 4 atoms, no lone pairs. Whenever you have 4 electron groups around your central atom, your electronic geometry will be tetrahedral. All right, that is a tetrahedral electronic geometry. And we know that whenever you have 0 lone pairs, your molecular geometry and electronic geometry are the same. All right, so you've got tetrahedral. Now, whenever you have a tetrahedron, that's the noun form, every tetrahedron is the same. You have 4 groups. 2 of them are going to be in the plane of the board, so we draw them as straight lines. 1 will be wedged coming out of the board. Sorry, I can do a better job than that. And 1 will be dashed going back away from you into the board or screen or page. We've got 3 4 hydrogens to add. So that is the three-dimensional representation. And the bond angles for a tetrahedron, the bond angle is 109 degrees. Doesn't matter which hydrogens you pick, it'll be the same no matter what. All right, and that is how you handle a pure tetrahedron. Let's take a look at what happens to the molecular geometries and the bond angles once we start adding lone pairs to the mix. Let's look at the molecular geometry for NH3. Now, our number of electron groups, we have 3 atoms on our central atom plus the 1 lone pair, so that's 4. That's 4 electron groups. When you know your number of electron groups, you instantly know your electronic geometry. We know this will be tetrahedral. All right? And when you know your electronic geometry, you can draw the start of your three-dimensional representation because every tetrahedron is the same. You're going to have 2 groups in the plane of the page or screen, 1 wedged coming out at you, 1 dashed going away from you. Now, we know we have 4 electron groups. 3 are atoms, 1 is a lone pair. And that lone pair will change your molecular geometry and your bond angle. All right? To find our molecular geometry, let's go ahead and add our pieces. I'm going to put my lone pair here. It doesn't matter where. You can put it anywhere. I think it would be easiest to visualize if I put it on top, which is why I selected it. So that is a representation of the electronic geometry. We know, however, the molecular geometry does not take into account the shape of the lone pairs, just the shape of the atom. So if we take that lone pair and just write it as a dot above nitrogen, this is the three-dimensional representation of the molecule. And if you look at it, this is a little hard to depict since we're not in the same room, but it kind of makes the shape that my fingers are making right here, where it's kind of like a pyramid, like this looking from the bottom, where you've got 3 vertices and they're all going up, whoa, off camera, going up towards the top. All right. So this shape, this geometry, when you have a tetrahedron with 1 lone pair, this is called trigonal pyramidal. All right, that is trigonal pyramidal. And that is the molecular geometry for NH3. Now, we've already seen what happened with trigonal planar. Once we added a lone pair, it pinched our bond angle down by 2 degrees. The same thing is going to happen here. A pure tetrahedron has bond angles of 109 degrees. So a trigonal pyramidal molecule will have a bond angle that is just slightly constricted 2 degrees. It'll have bond angles of 107 degrees. All right? So that is the three-dimensional representation, bond angle, and molecular geometry for ammonia, NH3. All right? We've seen what happens when we add 1 lone pair. Let's add another. Whoops. Let's determine the molecular geometry for water. All right. Now, we've got 2 atoms on our central atom, plus 2 lone pairs, so that is 4 electron groups. Once you know your electron groups, you know your electronic geometry. 4 electron groups means that your electronic geometry is tetrahedral. All right. And once you know your electronic geometry, you can begin to draw your three-dimensional representation because every tetrahedron is the same. You have 2 electron groups in the plane of the screen. One wedged coming out at you, one dashed going away from you. All right. Now, how many lone pairs do we have on our central atom? 2. All right. This is going to affect our molecular geometry and our bond angle. You can put these anywhere you'd like. I'm going to put my 2 H's there and my lone pairs here and here. Now we know when we're trying to figure out our molecular geometry, we're only concerned with the shape the atoms make. All right? So we're going to take our electrons and just represent them as dots on our central atom. All right? Just dots on our central atom. Now when you look at this shape, the shape that this makes, it might look reminiscent of when we had a trigonal planar geometry with 1 lone pair, because this kind of looks like a bent line again, and the molecular geometry here is indeed bent. Now you may be going, well, how does someone determine what's the difference then between a tetrahedral electronic geometry with 2 lone pairs and a trigonal planar electronic geometry with 1? And the answer is in the bond angle. We have 2 lone pairs, so this gets pinched down from our bond angle of 109 twice. We lose 2 degrees twice, so 4 degrees. So a bent tetrahedron has a bond angle of 105 degrees, whereas a bent trigonal planar molecule has a bond angle of 118. So it comes down to the bond angle. That's the difference between a bent tetrahedron and a bent trigonal planar atom. All right, and those are the molecular geometries, the 3 molecular geometries based on tetrahedral molecules. All right, let's look at phosphorus pentahydride. We've seen everything that can happen when you have 4 electron groups. What goes down when you can have 5? Every time you have 5 electron groups, your electronic geometry is trigonal bipyramidal. Trigonal bipyramidal. All right. Now, we have no lone pairs in play, and we know that whenever you have no lone pairs, your electronic geometry is the same as your molecular geometry. All right, these two are the same. Now, how do you draw this situation? The trigonal bipyramid is a little bit more of a challenge to draw. It's personally, it's my favorite molecular geometry. When I was in grad school, I was doing a reaction that involved a silicon atom that had trigonal bipyramidal geometry. It was super awesome. So I owe a huge debt and my degree to this geometry in particular. So I'm very excited whenever I get a chance to draw it. Now, here's how. When you draw a trigonal bipyramidal, I'm going to draw it down here just so we have a little more space. Every trigonal bipyramid is the same. It will have 3 electron groups in the plane, like so, the plane of the page, and then you kind of have those 2 vertical ones, and then the horizontal one. On the opposite side from the horizontal one, you will have a wedge coming out at you and a dash going back behind you. All right, now let's put our H's on. So this is the 3-dimensional representation of the trigonal bipyramid. Now let's talk bond angles. Another thing that makes this geometry cool is it is the first geometry that we've encountered that has more than one bond angle. For every one that we've seen before, all the bond angles are equal throughout the molecule. That is not the case here. There are two different bond angles because there are two different positions on the trigonal bipyramid. Now, these two, the kind of ones that are up and down, these positions are called, I'm going to write them over here. They're called axial, kind of the straight up, straight down situation. And the other three, these are called equatorial. You've got axial, you've got equatorial. The reason they're called these is kind of the ones that are straight up and down are, if you looked at this molecule and imagined it was like the planet, like Earth, those two H's would be sitting up on the axis, right, where the North Pole and South Pole is. And the three equatorial hydrogens are all kind of around where the equator of the molecule will be. So you've got your axial, where's my camera? There we go, right there at the poles. And you've got the equatorial kind of around the equator. Now, there are two bond angles in this molecule. The first is the bond angle that goes from an axial position to an equatorial position. All right? And this bond angle is a pure 90 degrees. All right, that axial to equatorial bond angle is a right angle. It is 90 degrees. The second type of bond angle is if you go from an equatorial position to another equatorial position, and this bond angle is 120 degrees. All right, so your axial to equatorial is 90. Your equatorial to equatorial is 120. All right? Okay, that is the trigonal bipyramid, the trigonal bipyramidal geometry. Let's take a look at what happens when we start adding lone pairs. All right, so first off, let's look at sulfur tetrahydride. So sulfur tetrahydride is a molecule with 5 electron groups. All right, 5 electron groups, one of which is a lone pair, right? 4 hydrogens and a lone pair on our central atom. Whenever you have 5 electron groups, automatically your electronic geometry is going to be trigonal bipyramidal. All right, and once you know that your geometry is trigonal bipyramidal, you can draw the start of the three-dimensional representation because every trigonal bipyramid is the same. You've got your 2 axial positions and then your equatorial positions, 1 in plane, 1 wedged, 1 dashed. The reason why, by the way, this is called trigonal bipyramid, a trigonal bipyramid or trigonal bipyramidal, is because it's kind of the shape is kind of two pyramids with 3 vertices kind of sandwiched together. If you like made a shape out of that, that's kind of what this molecule would look like. All right, now let's talk molecular geometry. Up to this point in time, I've always said when it comes to, so we've started our 3-dimensional representation, and I've always said it doesn't matter where you put all the lone pairs and atoms attached to it. Put them wherever you want, it's going to be fine. That has been true for every geometry before this one because every position was equal. They were all equivalent, and that's evidenced by the fact that all the bond angles are the same. on a trigonal bipyramid, it is not perfectly symmetric, and so it matters where you put your lone pairs. All right. When you are adding your lone pairs to a trigonal bipyramid, your lone pairs always go to the axial position. Nope. Always go to the equatorial position. They never go axial. And the reason why, we already know that electrons they create more repulsion than a bond. And so you want to put them in a place where they're further away from everything else, and that will always be in the equatorial position. So if we add our lone pair, and you can put it in any equatorial position, I'm going to put it here. All right. And then H's go everywhere else. Now, this is going to... so we know for our molecular geometry, we're only interested in the shape that the atoms make. So we don't look at the shape of the electrons, of the lone pairs, just the atoms. And this molecular geometry, now looking at it as I've drawn it, might be a little hard to see, but if you look at it, if I kind of draw it on its side, this might help it make more sense. It kind of looks like a teeter-totter or a seesaw. So the molecular geometry here is called seesaw. Now, the funny thing is this, it's called that because, well, that's kind of what it looks like. But this analogy is getting less and less useful as time goes on. For those of you who are in Gen Z, especially on the younger end of Gen Z, you may not have ever seen these. A seesaw was a piece of play equipment that they used to put in like parks and playgrounds that was, had like a seat like so, and it had a fulcrum, and two kids would sit on either side and go like me, 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 me. And use their weights to kind of go up and down. They don't put them in parks anymore because it turns out they're crazy dangerous. It's actually the first memory I ever have of like seeing a broken bone. We were at this park, and this brother and sister, older sister, little brother, were like on a seesaw, on a teeter-totter, going up and down, and the sister slammed her weight down hard and launched her brother, and he landed, and I heard this snap, this crack, and he starts screaming, and he got up, and I'll never forget it because his arm was like hanging, but like at a like 90-degree angle, and was like flapping around, but the skin was still attached. It was super gnarly. Anyways, this wasn't the only time something like that had happened, and so they no longer put seesaws or teeter-totters in parks. So if you look at this and you're like, I don't see a seesaw because I don't know what one is, Google it. I'm sure there's you can find YouTube things of kids doing dumb stuff on seesaws. But this is a seesaw geometry. We still have two bond angles to deal with. We have the equatorial to equatorial, and we have the equatorial to axial bond angles, and we've added one lone pair, so each gets pinched by 2 degrees. So we've got an 88-degree bond angle and a 118-degree bond angle in the seesaw geometry. All right. Yeah, it was nasty. All right, let's look at what happens to our trigonal bipyramid when we add 2 lone pairs. So if you look at chlorine trihydride, which is chlorine, 3 hydrogens, and 2 lone pairs. We have 5 electron groups. If you have 5 electron groups, you know that you are dealing with a trigonal bipyramid. And we can already start drawing our molecular or our 3-dimensional representation because we have 2 axial positions, 3 equatorial positions, and this will kind of be the scaffold for our molecule. All right, now we have 2 lone pairs in play, and we know that those lone pairs will always go to axial positions, and so you put your 2 lone pairs in, attach everything else, and we're on our way to determining our molecular geometry. Now we know that we need to only consider the shape the atoms make here. All right, and if you look at this molecule, this one's a little easier to see. And again, I'm going to kind of turn it on its side. But you'll notice that if you do turn it on its side, it kind of makes the shape of a T, and the molecular geometry was named. After that, this is called a T-shaped geometry. Now, there's only one bond angle here, and that is the bond angle between the 1 equatorial position with a hydrogen and the axial hydrogen. We've got 2 lone pairs, so it gets pinched down 86 degrees. This is the 3-dimensional representation of a T-shaped trigonal bipyramid. All right. Now, let's go ahead and we have time for one more. Let's look at yeah. Let's look at I3 minus. It's a polyatomic ion. Now, on our central atom, we have 2 atoms attached plus 3 lone pair electrons, which is 5 electron groups. Our electronic geometry is trigonal bipyramidal. And so we can start drawing our 3-dimensional representation because we've got the 2 axial positions and the 3 equatorial positions, and that will always be the case. Now, what do we do with our 3 lone pairs? We know that lone pairs always go to the axial position. So we got to put them down there, which means our lone pairs always go to the equatorial position, which means our iodines have to go axial. Now, to find the molecular geometry, we just want the shape that our atoms make. So we're going to turn all of our lone pair electron groups into just dots around our central atom. And you'll notice that this thing looks like a straight line. And it is. Because the 2 iodines are in the axial positions, right? They're at the pole, the north pole and the south pole, along the axis of the molecule. So this molecular geometry is linear. And the bond angle here is a pure 180. All right? Okay. So we have covered, I'd say about Let's see. 1, 2, 3. There I can do some exact math. So we have covered, at this point in time, we have covered 77% of VSEPR is complete at this moment in time. And given that there's 5 minutes left in lecture, we're going to pause here. In the next lecture, we'll do 6 electron groups, which is the octahedron, or octahedral geometry. And we'll look at the octahedron with no lone pairs, and then when we add lone pairs, how it affects it. We'll do that next lecture, just because I don't want to rush things, and we'll pick up from there. As of this moment in time, though, you can handle any what's the word I'm looking for? You can assign the molecular geometry and bond angle for any molecule that has 5 electron groups around the central atom or fewer. So you can start practicing. You can do 77% of the problems. If you notice that there are 6 electron groups, you can read on your own, or wait till Monday's lecture and we'll cover how to handle octahedrons at that time. Alrighty, so we'll go ahead and wrap up there. Hopefully I'll see some of you in office hours tonight. If I don't, I hope you all have a great weekend, and I'll catch you on Monday. Later.